So what we have is that the sum of mi ui, where ui, remember, is the velocity of each particle, the ith particle, measured in the center of mass frame. That sum is then the total momentum measured in the center of mass frame, and that is 0. Remember, this came about because all of the internal forces canceled out. The external forces caused the motion of the center of mass, but from the center of mass frame, the total momentum in the center of mass frame is 0 because all of those internal forces, they always came in pairs and they would always cancel out. And they cancel out if they're conservative forces and non-conservative forces. So even the existence of non-conservative forces is not going to change the fact that the total momentum in the center of mass frame is 0. Non-conservative forces might lose energy, they might take energy out of the system, but they are not going to change the momentum. Let's take a look how the kinetic energy of the system is related to the center of mass frame. What is the total kinetic energy of the system? Well, we can find the kinetic energy of each particle, 1/2 mi vi squared, and then we add them all up for all the particles. Let's put this in terms of the velocity relative to the center of mass. The velocity of the center of mass and the velocity relative to the center of mass. Well, we could do that by writing this out as a dot product. So this is the sum of 1/2 mi vi squared, that's the magnitude of the velocity squared, which we know is vi vector dotted into vi vector. Now, vi vector we're going to write in terms of that combination of the velocity of the center of mass and the velocity relative to the center of mass. This is sum of 1/2 mi. Vi is ui plus vcm. In other words, the velocity relative to the center of mass plus the velocity of the center of mass. That's vi, and then we have to dot that into itself, ui plus vcm. And then what do we get when we dot those together? We're going to get equals sum of 1/2 mi. We're going to take the dot product of the first, dot it into the first. So ui dotted into ui, so that's ui squared. Then we'll take ui dotted into vcm, and then plus vcm dotted into ui, but the order doesn't matter, so it's going to be the same. So we'll write this as 2 times vcm, I said 2, but I didn't even write the 2, plus 2 times vcm dotted into ui. Okay, and then plus vcm dotted into vcm, that's going to be vcm squared. Okay, now let's separate this out. What do we get? We get, this is the sum of 1/2 mi times ui squared. Okay, that's the first term. Now I'm going to write the last term. Bring that vcm. Now the velocity of the center of mass, that does not depend on each particle I. That will be a constant for each I. That might be changing, possibly, but it's not going to be changing over the sum for I, so I can pull that out of the sum for I. So I'll write this as plus 1/2, vcm squared times the sum of mi plus the sum of 1/2 mi times 2 times vcm dotted into ui. vcm dotted into ui. Okay? Now, let's look at this. What do we have? We've got the sum of 1/2 mi ui. So that would be, what's 1/2 mi ui? That would be the kinetic energy of each particle measured in the center of mass frame. So that would be the kinetic energy of each particle in the center of mass frame. I'm going to just leave that the way it is for now. 1/2 mi squared. All right, now what's this? Well, the sum is just over mi. Sum of mi, that's just the total mass. So this is 1/2 plus 1/2 total mass, vcm squared. Now let's look at this. Well, the 2's cancel. And we've got VCM dotted into UI. But like we said before, the VCM is constant for each I. It's the same VCM. So I'm going to pull that out, and I'm going to write this as VCM dotted into the sum of MI UI. But wait a second, the sum of MI UI, that's what we saw before. That's the total momentum of the system measured in the center of mass frame, which we saw to be 0. So this sum right here is 0. So we can take that out. So what do we end up with? We end up with a very simple result. What do these two terms mean? We talked about this one. This is the kinetic energy of each particle measured relative to the center of mass. So we'll write that as kinetic energy relative. In other words, relative to the center of mass. Plus 1/2 mvcm squared. So this is the total mass times the velocity of the center of mass squared. This looks like the kinetic energy of the center of mass itself. So it's like the kinetic energy of the system, where we just think of the whole system at the center of mass, and the center of mass is moving. So that's like the kinetic energy of the center of mass. Let's keep in mind that these velocities, the velocity of each particle, depends on what frame we choose. Remember our original frame that we chose to determine the positions of the velocities of the particles? The velocities depend on the frame we choose. So down here, this term, the velocity, the kinetic energy relative to the frame of mass, that does not depend on the frame, because that is by definition defined in the center of mass frame. This term over here, this is what changes if you change your frame of reference. For example, if you go into the center of mass frame, what's the velocity of the center of mass? In the center of mass frame, it's 0. So this will be 0. This will be 0. So the kinetic energy of the center of mass will be 0 if you're in the center of mass frame. Okay, we have just covered quite a bit of theoretical material. Let's stick some numbers in here and take a look at some examples. Let's look at a one-dimensional problem with just 2 masses. Let's imagine we have M1 is 1 kilogram and M2 is 3 kilograms. Even before we start looking at the velocities, we've already looked at where the center of mass of this thing would be, and we know that it would be about 3/4 of the way towards M2. So it's going to be over here somewhere. But M1 and M2 are moving, so the center of mass is also going to be moving. It's not stationary. So here's the center of mass. Let's figure out what is the velocity of the center of mass. So how are we going to do that? Well, we know that the total mass times the velocity of the center of mass is equal to the sum of m1 v1 for each particle. So we'll have m1 v1 plus m2 v2. Let's imagine m1 is moving to the right at 4 meters per second, and m2 is moving to the right at 8 meters per second. So what do we get here? We get m1 is 1 kilogram times v1, 4 meters per second, x hat, plus m2, which is 3 kilograms, times v2, which is 8 meters per second, x hat. And what do we get? So we get 3 times 8 is 24, plus 4 is 28. So this is 28 kilogram meters per second, x hat. In other words, that's the total momentum, really, remember? So this would be P total. Not measured in the center of mass frame, but in our frame that we have set up where these two numbers are the velocity. So we might say in the classroom frame. Now we know this must be the total mass. What's the total mass? 1 plus 3 is 4 kilograms. So this is 4 kilograms times VCM. So we divide by 4 kilograms, and what do we have? We have VCM is equal to 28 divided by 4, or 7 meters per second, x hat. So what this is telling us is that our center of mass is then moving to the right, positive, moving to the right at 7 meters per second. Okay, very good. Let's take a look at this from our center of mass. Oh, well, actually, wait, sorry. Before we do that, let's figure out what's the kinetic energy. Before we move to the center of mass frame, let's figure out what our total kinetic energy is. So K total will be the kinetic energy of our first mass, so that'll be 1/2 m, 1 kilogram, times v squared, so 4 meters per second squared. That's the kinetic energy of our first mass. What's the kinetic energy of our second mass? 1/2 m, which is 3 kilograms, times v, which is 8 meters per second squared. Okay, multiply that all out. 1/2 times 1 times 16 plus 1 times 3 times 64. And what do we get? We get 104. 104. Great. Let's figure out what is the kinetic energy of the center of mass. In other words, what's the kinetic energy assuming all the mass is located at the center of mass and moving along with it? What do we have in that case? So the kinetic energy of the center of mass will be 1/2 times the total mass times the velocity of the center of mass squared, which is 1/2 times the total mass, 1 plus 3, 4 kilograms, times the velocity of the center of mass, which is 7 meters per second squared. So we multiply that out, 1/2 times 4 times 7 squared, 49, gives us 98. Great. Now, let's move this problem into the center of mass frame. What do we have? We've got the center of mass is moving that way at 7 meters per second. So what are these velocities gonna look like? What I'll do is I'll write it next to them. So we're gonna subtract 7 meters per second from every velocity. So what do we get? We'll get u1 is equal to 4 minus 7, that'll be -3 meters per second, x hat. So it looks like this one is going that way. What about this one? We'll have 8 minus 7, that's 1. So we'll have u2 equals 1 meter per second, x hat. So in the center of mass frame, this mass is going that way, this mass is going that way. And then what's the center of mass doing? What's the speed of the center of mass? U center of mass will be 7 minus 7 equals 0. Well, that's exactly what we should have thought. The velocity of the center of mass is 0 in the center of mass frame. Okay, good. So what are the momenta? What's the total momentum in the center of mass frame? And then what's the relative kinetic energy in the center of mass frame? And let's see what we get. Well, what is the momentum of the object in the center of mass frame for mass 1? What is P1 center of mass? So it's going to be m1 times u1, so 1 times -3 kilogram meters per second x hat. So that's the momentum of object 1 in the center of mass frame. What is P2 center of mass? P2 center of mass, that's going to be m2 times u2. So 3 times 1, that's 3 kilogram meters per second x hat. What is the total momentum in the center of mass frame? Well, it'll be the sum of these. -3 plus 3 is 0. The total momentum of the system in the center of mass frame is 0. Well, okay, that's what we said. That's what we said. That's what we thought would happen. What is the kinetic energy? So what is K1? This would be K1 relative. In other words, the kinetic energy of mass 1 relative to the center of mass. So we're going to use U here. We'll have 1/2 times 1 times U1 squared. So this will be 1/2 times 1 kilogram times -3 meters per second squared. And what do we get? We get 3 squared is 9 times 1/2, 4.5. So this will be 4.5 joules. That's K1 relative. What's K2 relative? K2 rel, this will be 1/2 times M2, 3 kilograms, times U2, which is 1 meters per second squared. And what do we get? 1 squared is 1. 1/2 times 3, 1.5. 1.5 joules. What is the total kinetic energy relative? So the energy of mass 1 relative is 4.5 joules. Energy of mass 2 relative is 1.5. What's 4.5 and 1.5? That's 6. And what do we notice? The kinetic energy of the center of mass plus the kinetic energy relative to the center of mass would be 98 plus 6, which is 104, which is exactly what we calculated the first time. Very, very good. Excellent. That is enough for today, I think. Next time, we're going to take a look at a different class of problems called collisions. In this problem, we looked at the motion of two masses, but in the center of mass frame, they were actually moving apart from each other, moving away. In a collision problem, we're going to assume that the masses are actually coming together, and then their internal forces are going to dominate the motion. We'll see you next time.